Good evening to all. Today we are going to discuss about thermodynamic process of constant volume, that is called isochoric process. So in this process we will try to understand what is work done, what is energy transfer, and finally we'll also find out heat transfer and the entropy change for the ideal gas. So let's begin the discussion for thermodynamic process for the constant volume process. So before that, let's understand about the thermodynamic system. Thermodynamic system is a focal point is the gas. Gas can be air, gas can be hydrocarbon. Some sign convention when work done on the gas or on the thermodynamic system is positive. When work, sorry, when heat transfer to the heat transfer on the thermodynamic system is positive. Heat transfer or taken from the system is negative. Work done by the system is positive. Work done on the system is negative. Energy increase of system is positive. Energy level decrease is called negative. So focal point is thermodynamic system is gas. Types of thermodynamic system, it is open system, closed system, and isolated system. In case of open system, there is a flow of masses and energy exchange for the open system. In case of closed system, there is no exchange of the mass but only the energy exchange. In case of isolated system, there neither there is exchange of mass nor the energy, so it is called isolated system. Ideal gasification state PV is equal to nRUT. On simplification we can write P small v RT, where P is pressure, V is a specific volume, R is a gas constant, T is the temperature. Work done on a closed system. For the closed system, work done is written at under integration of PdV, and area under the curve on x-axis, that is on PV diagram, is called work done or work transfer. Similarly, on the open system, it is written as a minus VdP, and area under the curve on y-axis is called, that is in PV diagram on y-axis, is called the work done on for the open system. And work done by the system is positive, work done on the system is negative, and work done per unit mass is called the work head or head. Energy transfer. Energy transfer the closed system is called internal energy change, and which is expressed as in energy change for the closed system is equal to underscore of CVD, sorry, integration of CVDT. Energy transfer for the open system is called enthalpy change. So energy transfer for the open system is written as integration of CPDT. Energy of the system increases is positive, energy of system decreases is considered negative. First law of thermodynamics can be used to find out the heat transfer. So heat transfer is equal to work transfer plus energy transfer. So Q is equal to W plus C. Please note that the first law of thermodynamics assumes the efficiency of thermodynamic machines is 100%, means there is no losses during transfer of work, transfer of energy, and or heat. So first law of thermodynamics consider everything ideal, there is no losses, 100% efficient. Constant volume process is also called isochoric process for the ideal gas. Let's say the in constant volume on PV diagram, you can see the 1 and 2 process, constant volume. Similarly, 1 and 2 process is also. So in this process, heat is added. In this process, heat is removed. Similarly, for TS diagram, you can see 1 and 2, heat is added, temperature increases, entropy increases. 2 and 1 is again heat is removed, entropy drops on TS diagram. So work transfer per unit mass for the closed system. You can write V is constant, so you can write PV is equal to RT, P1 is RT1, and P2 is RT2. So P2 by P1 is equal to T2 by T1, and also you can use Cp minus Cv is equal to R for ideal gas. Work done for the closed system PdV, since there is no change of volume, so work is zero. You can see area under the curve on x-axis is zero because it is straight line, and that is why work transfer per unit mass is 0, and as well as total work transfer is also 0, because if you multiply mass it will also 0. Now constant volume process for the energy transfer for the closed system, we can written as integration of CVDT. So CVT2 minus T1 is the energy transfer per unit mass. total mass, total energy transfer is equal to E is equal to m into CV T2 minus T1. Heat transfer, as per first law of thermodynamics, Q is equal to W plus E. W is 0, so Q is equal to CV T2 minus T1. So heat transfer per unit mass Q is equal to CV T2 minus T1. For total heat transfer, M into CV T2 minus T1. You can see area under the curve on x-axis, on TS diagram, it will give the heat transfer. So you can see the heat transfer in this process. Now entropy change 1 and 2 and 2 and 1. Entropy change is just equal to Q upon T. Q is CV. Q is equal to CV T2 minus T1. So we can write CV dt. And entropy is equal to CV upon T into dt. So we can write CV log dt. So log dt means ln. You can short natural log, in short is written as ln. So you can write entropy change per unit mass S equal to CV ln T2 by T1, and total entropy change S is equal to m into CV ln T2 by T1. You can see the graph because of increase. The graph is drawn based on this equation. So entropy change is based on the temperature ratio. So if temperature ratio increases, entropy increases. If temperature decreases, entropy decreases, as per this equation. Now the constant, what is called constant volume process for the open system. So again, the volume will remain same. PV is equal to RT, P1 V1 RT1, P2 V2 RT2. So P2 by P1 is equal to P2 by T1. Cp minus Cv is squared. This is another relationship. Work done minus VdP. So we can write minus V P2 minus P1. So P1 minus P2. So W P1 V into 1 upon 1 minus P2 by P1. So we can write W is equal to P1 V1 bracket 1 minus P2 by P1, but we can replace P1 V1 is equal to RT1. So RT1 into 1 minus T2 by T1, because T2 by T1, P2 by P1 can be replaced as T2 by T1. So we can write R is equal to, W is equal to R into T1 minus T2. So this is the work transfer per unit mass. W is equal to R T1 minus T2, and total work transfer mass into R into T1 minus T2. This is for open system. Energy transfer, we can write Cp dt, because for the open system, so E is equal to Cp T2 minus T1. For total mass, M into Cp T2 minus T1. So heat transfer, as per the first law of thermodynamics, Q is equal to work plus W plus E. So you can add this, and so we can write, taking out T2 minus T1 is common, Cp minus R. Cp minus R is Cv. So we can write Q is equal to Cv T2 minus T1. So heat transfer per unit mass Q Cv into T2 minus T1. For total mass, total heat transfer mass into M into Cv T2 minus T1. This is for area under the curve. Again, it will give the heat transfer on X. Area under the curve on x-axis give the heat transfer. Entropy change, we can write Q upon T. Q is Cv T2 minus T1. So Cv dt. Cv upon T into dt. So Cv 1 upon T. So 1 upon T dt is a log, that is ln. So Cv ln T2 minus T2 upon T1. So this is the entropy change per unit mass. For total mass, you have to multiply M, and this graph is drawn on TS diagram based on this equation. Temperature ratio increases, entropy increases. Temperature ratio decreases, entropy decreases. So let's understand with an example. Nitrogen gas has initial pressure and temperature R, 0.5 bar gauge, 30 degrees Celsius respectively. Heat is added to thermodynamic system such that the final pressure reaches to 0.80 bar gauge on constant volume process. With consideration of ideal gas, calculate work, heat, energy transfer and entropy change during this process. For consideration of closed and open system, also calculate the inlet and outlet specific volume. Following data are given: mole weight of nitrogen 28 kg per kilomole, universal gas constant 8314.5 joule per kilomole per Kelvin, specific heat capacity at constant volume 20.86 kilojoule per kilomole per Kelvin, local barometric pressure is 1 bar absolute. So now we solve this question. These are the given for the constant volume pressure, local barometric pressure, absolute temperature, inlet pressure P1 is gauge plus PA, that is local barometric pressure, which is added 1.5. Temperature 30 degree. Outer pressure is 1.8 because 0. 0.8 plus 1 is 1.8. Mole weight is given. A specific heat capacity at constant volume CV is given, and universal gas constant 8314.5 is also given. Now we need to do calculation. Gas constant RU upon M, it is calculated 297. A specific heat capacity at constant volume CV, converting into joule per kg per Kelvin by dividing M, it is 745. And at constant pressure CP CV plus R, you add these two, it becomes this. A specific heat capacity ratio K is CP upon CV, we can see 1.4. The inlet specific volume V1 is calculated this, and temperature is also calculated this 90.6 degrees Celsius because 273.5 is minus. Work done is 0 because it is constant, because it is a closed system. Heat energy transfer is CVDT, it is 45,169. Heat transfer will be same because summation of these two, and entropy change will be 136 joule per joule per kg per Kelvin. For the open system, the only change will be the work transfer, which is coming as R into T1 minus T2 is minus 18,004, and energy transfer is 63,173, and heat transfer will be summation of these two, or we can write CV T2 minus T1, which is 45,169, and entropy change is 136. So I hope you have enjoyed this session for constant volume process. Thank you for watching.